Thank you very much, Elena, for introducing me. And also, thank you, Wojtek and Eva, for arranging this online session for me. Okay, I will talk about the true design for catalysis, but that is just challenging, and not we have not yet get the goal of this true design. So I'm very pleased if you get the hint for true design. I'm very happy to do that. Okay, so in my understanding, the material design of material must be studied by um, sorry by describing the preferable structure. So this is the starting point of material design. Without describing the preferable structure, it is impossible to start any discussion. So then, for example, this is a very famous toxic compound extracted from sea animal. So uh, this is described. This This is the name of this compound, and this shows the structure of this material completely. So this is the unique name, only showing this structure. So this palytoxin, that is the regular name, but that is described as this very, very long name. So that means structure of organic molecule is describable, that is completely describable. So it is possible to identify this compound by using that name. However, for inorganic solids, that is a bit or very difficult. So that is the indescribable. So that is very, very difficult to describe the structure of inorganic solid. But this is not undescribable. Undescribable means completely impossible. A bit, very, very difficult, but not completely undescribable. Okay, so then why it is difficult to describe the structure of inorganic solid? So at least it is necessary to describe the structure of bulk. And you can say that the crystalline structure can be described as the name, for example, anatase and rutile from XRD analysis. However, every solid, I think at least a small part is amorphous, and it is impossible to describe this amorphous part. And also, the surface structure is very difficult to describe what kind of surface is exposed and the area, size of area, and also how those exposed facets are interconnected. It is rather difficult to describe. And also the size. You know that the particle size has distribution, and it is necessary to describe all those distributions. So how can we describe those structure of solid materials? So then we put the data of as a structure of solid materials, crystalline phase, primary particle size, secondary particle size, the specific surface area. This is almost all the possible characterization method. And even though that the specific surface area, this term contains surface, there is no surface structural information. So that means we have no surface structural information for solid inorganic materials. So therefore, it is rather difficult. And that is due to the lack of usable analytical method. For solid materials, so many analytical methods are there, and that is categorized into those parts: surface, bulk, macroscopic, and microscopic. And for surface structure, there are almost no macroscopic surface structural analysis. There are some those measurement methods, but that the target is limited and the information is not so much. So therefore, we cannot have the surface structural properties for solid materials. So then, about 10 years ago, we have proposed that ERDT CBB pattern can be information, including the macroscopic surface structure. And if we can use this, no other analytical method, analytical data is not necessary for this. So what is ERDT? That is energy reserved distribution of electron traps. And the CBB is conduction band bottom. All these are energy distribution. And those data can be obtained by RDB-PAS. So before interpretation of RDB-PAS, I will tell you about what is electron traps. Probably all of you know that the titanium oxide, when that is UV irradiated in the presence of donor, that the white powder is converted into blue or blue-gray powder. So that is due to Ti3 formation. That means the part of Ti4 ion in TiO2 accept electron to become Ti3 plus. So such a site accepting electron is called electron trap. So metal oxide, including titanium, tungsten, molybdenum, something, all these metal oxide powders change the color when irradiated in the presence of donor. So therefore, all these metal oxide, almost all the metal oxide has electron traps. And if that is measured easily, it gave the information. So then we prepared the new methodology, reversed double beam photoacoustic spectroscopy. So electron trap that can be is vacant electronic state in metal oxide powders, and electron in valence band is directly excited to electron traps to fill up the electron trap with electron, and this change the color of sample, and this change of color is detected by photoacoustic spectroscopy. Two beams are used. One is for excitation from electron from valence band to electron trap. The other modulated light is used for detection of change of color. So this is the setup, and similar to the XRD, the samples can be loaded like this, and then set in the PA cell, photoacoustic cell, and the two beams are combined to introduce to the samples. And left top one is the scanning of excitation wavelengths from longer wavelength side to shorter. So at the 450 nanometer, the electron trap filling started and then filled up, and at about 350 nanometer, that is almost saturated. By differentiation from this spectrum from longer wavelength side, this is the energy reserved distribution of electron trap in relative scale. And that is the conversion coefficient is calculated from the other photochemical method. This is converted into absolute density of electron traps. And then only using the one modulated light beam, so ordinary PA spectrum, it is possible to get the diffusion diffusion reflectance spectrum like spectrum. From this, the band gap, that is conduction band bottom and the difference with between conduction band bottom and valence band top. And electron trap filling start by the excitation from valence band. So therefore, energy of electron traps are shown in difference to valence band top position. So therefore, electron trap distribution and also conduction band bottom position can be plotted in the same figure. And 152, that is the total density of electron traps. And this is titanium oxide. And without showing the specific surface area or anatase and the small router crystalline structure, without knowing those information, it is possible to see only by seeing this pattern that is something kind of titanium oxide with the named STA4. So this is the example of titanium oxide samples. All these pattern contains ERDT, CBB, and TD, at least three parameters. And anatase and the small anatase with small amount of router with small amount anatase, and router and brookite. And the pattern seems depends on the crystalline structure. However, the amorphous, that is completely amorphous, but the composition is TiO2 and no X-ray XRD peak. So this also shows the pattern, similar pattern, but a bit higher energy. So therefore, not only crystalline, but also amorphous shows this. And important point is the total density of electron traps are almost proportional, not completely, but almost proportional to specific surface area. This means that electron traps are located on the surface and they are not something like a point defects. That is on the surface reconstruction structure. So then, for example, anatase only sample, left top one, that is the CBB position is almost the same. So therefore, CBB position shows the bulk structure. And for router case, similar to this anatase, the CBB position is almost the same, so reflecting the bulk structure of router. But anatase with router samples shows a bit different CBB position that depends on the bulk structure. And for example, anatase only sample and left the top one, the TiO1 and the TiO13 has almost the same specific surface area. However, the ERDT pattern is completely different. So that means they are almost the same particle size, but the surface structure is not the same. So therefore, it is possible to say that those patterns can be used as a fingerprint of titanium oxide samples. So even if all these are TiO2, but the pattern is completely different. So then, why that can be our fingerprint? So that is at least three parameters is necessary to identify the solid materials. One is bulk structure, one is size, and one is surface structure. So ERDT-CB pattern contains all these parameters. ERDT reflect the surface structure, CBB reflect the bulk structure, and the total density reflect the size or specific surface area. So therefore, those pattern contains all the necessary parameters for identification of solid materials. So then the RDB-PAS can be a new analytical method for macroscopic surface structure. So then probably you know that the crystal, previously millennium active PC series titania. I understood that different PC10, 50, 100, something. So they are almost the same structure, but only the particle size is different. However, checking this ERDT pattern, there is the difference between PC50 and 100. So that means they are in different size, a different specific surface area at the same, but the surface structure is a bit different. So therefore, depending on the size of material, that is a bit different in surface structure. Not only titanium oxide, the other kind of metal oxide shows the different ERDT pattern. The important point is, even if for example, here in tungsten oxide, different the sample from different supplier shows a bit different pattern. So that means even if the same composition, the surface structure is different depending on the preparation method or storage method. And the other kind of metal oxide also shows. And for example, tin oxide, that has a bit complicated spectrum. That means some impurity of low valency, SN2 plus of something. So therefore, it is possible to see that the actual difference in surface structure. And not limited to metal oxide, carbon nitride that can be used for photocatalyst, that can be measured by using RDB-PAS to give ERDT pattern. So this is the collaboration work with Professor Sasaki, previously Kyushu University. Now she is working in Waseda University. They prepare the sample of C3N4 from different precursors containing heteroatoms. But the product is almost the same if the XRD pattern is observed. So almost the same XRD patterns. That means the bulk structure of those samples are almost the same, even if the different type of precursor was used. But ERDT pattern is completely different. So for the CBB position is not so much different, but oxygen-containing precursor gave the low energy peaks here. And also, if the carbon nitride prepared from only CN-containing precursor, if that is treated in air, the similar low energy peak appears. And also, sulfur-containing precursor gives these low energy peak. So if I have time in the last part of my talk, I will tell you that this low energy peak is N-deficient compound. So that not the N proportion is a bit lower than the bulk structure. So those heteroatom containing precursor gives the change of surface structure. And to check the similarity or identicalness of those ERDT CBB pattern, we check the similarity quantitatively measured the similarity of samples. This is the result of one kind of commercial titanium oxide. To measure this RDB-PAS measurement, I asked the graduate student to take a sample from almost the same position in the same bottle. And he measured the same sample 3 times, and almost the same patterns could be obtained. And to compare to check the similarity of those patterns, 3 parameters. One is the ERD pattern shape matching. That is the shape of peak, not absolute value. And the second one is the total density, zeta day. And the last one is conduction band bottom position. By putting the weight, the total degree of coincidence, zeta value, is calculated from this equation. And those 3 pairs of samples shows degree of coincidence almost higher than 0.9. The highest one is 0.95. And that means those samples are taken from almost the same position in the same bottle. So therefore, if the zeta value calculated by using this equation is higher than 0.9, that we can say that those 2 samples are identical, the same. But if the sample is taken from a bit different position, the shape is clearly different, and zeta value is decreased to almost 0.7, from 0.9 to 0.7. So that means 2 points. One is this measurement is very, very sensitive to especially surface structure. And the second point is, even if in the same bottle, the sample is a bit different, probably the surface structure or in the, surface water might give such a difference. So therefore, it is necessary to think even in the same bottle, the content is a bit heterogeneous. And then we check the very large number of titanium oxide by pairing the pairs of those titanium oxide samples. And this plot, the x-axis is the zeta value of pairs of titanium oxide. So 1 means almost the same. The 0 means completely different. And the y-axis is photocatalytic activity for those 3 kinds of reaction, including hydrogen evolution, carbon dioxide evolution, and oxygen evolution. And they are plotted. This plot is a pair of titanium oxide, and actually almost no relation between them. However, here is a line. This means the pairs of higher degree of coincidence didn't give low zeta PC, photocatalytic activity. That means the similar photocatalyst, titanium oxide, shows similar photocatalytic activity. By taking the moving average, we can obtain this plot. So this plot says that if the zeta value is lower than 0.6, that is zigzag, accidentally high or accidentally low. But if zeta value is higher than 0.6, that is increasing. And it is expected that if the zeta value is higher than 0.8, zeta PC value may become almost 1. So that means if the zeta value is higher than 0.8, that they are almost identical, the same titanium oxide. So therefore, that can be the photocatalytic activity must be almost the same. So this zeta value is a very good index for similarity or identicalness of titanium oxide photocatalyst. The important point is if same ERDT CBV patterns are obtained, that must show the same property of or activities because they are identical. And if the different activity or property is obtained, they must show different ERDT CBV pattern because they are different. So therefore, even if the different ERDT CBV pattern is obtained, we cannot say anything for property or activities. However, we have found that a very important point. We checked the ERDT CBV pattern for those three photocatalytic reactions, and the pattern is arranged in the order of photocatalytic activity. Left top is the highest, and the left bottom is the lowest activity. And the number figures shows the relative photocatalytic activity in reference to the highest activity sample, 100. And except for hydrogen evolution case, CO2 evolution reaction and the oxygen evolution reactions, the top photocatalyst showing the relative activity higher than 70% gave almost the same ERDT CBV pattern. In the other words, the lower activity samples are not the same. So that means the activity lower is different properties. Sometimes lower specific surface area or the band gap or something. So many parameters affect the photocatalytic activity. And for low activity samples, the reason is different depending on those samples. However, higher one is the highest. The property is almost the same, and that is highest. So that is very important point. So the photocatalytic activity seems determined only one parameter. So the minimum activity, the activity is lowered only one parameter. Even if the other parameter is high, the lower parameter decreased photocatalytic activity. So there is the very famous the sample that is the Liebig's law of minimum. So Liebig, that is the name of condenser. The Liebig found that the plant growth is the rate of plant growth is controlled by the minimum parameter. And so many parameters, sunshine, waterfall, rainfall, something. But the plant growth rate is determined by the minimum parameter. Even if the other parameter is high, the minimum parameter determines the activity, the plant growth. So this is the same for photocatalyst. So therefore, it is a bit difficult, a bit different from the ordinary, analysis of data. So at least we remember this point. Okay, then those ERDT-CB pattern can be a fingerprint, but fingerprint is just a fingerprint. There is no actual information of surface structure. So then we noticed this pattern. So this is the very wide range peaks. And actually, it seems that that is, this pattern is a summation of different peaks. And we assumed 5 Gaussian peaks for fitting the data. And this is deconvoluted into 5 peaks. And I have no time to interpret how to assign these peaks, but they are assigned to amorphous. The highest energy one, red one, is amorphous, and yellow one is amorphous on anatase, and anatase, green one, and blue one is anatase or amorphous on rutile surface, and the violet one is rutile surface. So this sample, STF1, contains all these surfaces. So this is very, very, how to say, not so clean surface. And then all these ERDT CBB patterns can be changed to like this. So many informations are obtained in this. And yesterday, the collaborator, Dr. Takashima, my son, interpreted this pattern, the AI or machine learning results of this analysis of those ERDT, deconvoluted ERDT CBB pattern. And full paper will be published soon. But today, I will show a bit the small part. So the top one, in the center, you can see the red peaks, the large red peaks. That is the small anatase particles. Small anatase particle has almost covered with amorphous phase. Thin layer, yellow one, the thin layer amorphous, and the red one is a very thick layer of amorphous. So small anatase particle, the inside might be anatase crystalline, but that is completely covered with amorphous. And you cannot see the violet only patterns. That means the rutile exposing only rutile surface. We cannot obtain any, all these rutile samples contains the other part, not rutile surface. And also almost no anatase surface only samples. The bottom right one, the green one, this one, green one, that is laboratory made samples. And almost all surfaces are covered with anatase, and that is octahedral particle. But small part of amorphous still on the surface. So therefore, almost no sample, pure anatase and pure rutile sample can be obtained. And for rutile samples, this composition, anatase rutile amorphous composition is calculated from by XRD. And if the amorphous content is lower than 6%, the surface is almost rutile with amorphous, but almost all the surface are exposed with rutile surface. However, if the amorphous content is higher than 6%, in those samples, the specific surface area is a bit higher than the smaller particles. And in this case, the small rutile particles is almost covered with amorphous. So this is completely different from those large rutile particles. So it is a bit it is necessary to notice this point if we discuss the activity of rutile samples. And I have not so much time, but I will show the ceria SCeO2 samples. So different from titania, only one kind of crystalline phase are seen in ceria SCeO2 samples. And this can be a thing for galleries, but almost all researchers in the field of catalyst use this as a catalyst, not photocatalyst. And so many papers have been published for the difference of activity depending on the particle shape, morphology. And the collaborator in Greece prepared 5 different kind of morphology samples. We checked this by using RDB-PAS and obtained those patterns, and that is deconvoluted into 5 peaks. And I have no time to interpret why we assign, but the 5 peaks, the higher energy one is amorphous, and 100 phase, 110 phase, 111 phase, and low valency, for example, CE2O3 surface. So those samples, the main peak is different depending on the morphology. And so then the cubic sample, so the many papers reported this as a cubic, only showing 100 facet. And octahedron particle, the center one, that is exposing only 111 phase. But actually, that is not solely exposing 111. So then we introduced the average morphology, and starting from regular and semi-regular polyhedrons with the 100, 110, and 111 proportion ratio can be obtained from these. So from the ratio of exposed facet, we can introduce the average morphology. And actually, cubic sample, NC, is not a complete cube. That is edge-shaped one. And NO, and the important point is this radar chart. That is the first example of showing the proportion, quantitative measure, proportion of exposed surface facet. And by checking this radar chart, it is possible to see the actual morphology. Okay, so then previously, the surface structure and the amorphous phase are neglected in the discussion of photocatalytic activity. However, by highlighting the surface structure of amorphous obtained by ERDT CBV pattern, we think it possible to discuss more deeply. For example, titanium oxide sample. This is a collaboration work with Slovenian researchers. This peak, 2-point blue-violet peak. This is important. So the photocatalytic activity that is amorphous on anatase peak, that if the proportion of this peak is high, the photocatalytic activity is high. So amorphous is important. Previously, we thought that amorphous phase is not so good because they may induce the recombination of electron and positive hole. However, this result shows that amorphous phase is important. And also tin oxide, SNO2 case, the surface, if the surface is covered with almost completely covered with amorphous phase, that is highly active. And for bismuth tungsten mixed oxide case, the sample is prepared to obtain bismuth tungstate single phase. However, the inside, the bulk structure is just a bismuth tungstate single phase. However, the surface is completely different depending on the preparation method and after treatment. So that means the surface structure is completely changed, and this must give the photocatalytic activity. And for strontium titanate case, this is not published yet, but commercial samples contains so many peaks. We have not assigned those peaks, but the surface of strontium titanate is not so simple. And if that is flux treated, so Professor Domen introduced this method to have highly active photocatalysts, but this induces so much difference for the samples and gives the different peaks. So the surface structure is completely different, and no SRTI03 surface is not only those surfaces, the other kind of surface as exposed. Okay, so studied highlighting the surface structures and the amorphous, we can reach a bit still long path, but we have how to say reaching to the goal of true design of photocatalyst. Thank you very much. This is the collaboration work with Professor Takashima, and if you have a question, please ask her in the conference site. Thank you very much for your kind attention.